Welcome, I'm Alex. This is the first video in a series about collision detection. In this video we will discover coarse collision bounding objects for early decision on colliding objects. These bounds are fastly constructed and tested against. So let's get started. Say we control a dinosaur. How would we be able to have the animal walk on a ground or be able to test if a villain left some toxic cloud in our character's face? Or if we actually lasered the villain to the ground? Addressing those tasks, we need to reduce the complexity on collision testing. Testing every point for every time step in-game will quickly become the bottleneck of our application. So we need to reduce complexity by introducing coarse bounding regions. Every object in-game could be enclosed by a box, for example. That box could be tested first for collision, and if any collision happened, further and more detailed collision detection could take place. For this video, we restrict ourselves on coarse collision objects we can test against. First, we start with a point in space. A point simply is represented by a vector in any coordinate system and originates from any basis. Our vector here is named C, and it can also represent the center of any other object like a circle. A circle is usually represented by a radius. Any point P on the circle can be constructed using the explicit form. We can also construct an implicit form from the explicit equation by computing the squared length of the difference vector and equating it to the squared radius. The circle is a very coarse bounding region but can be constructed very quickly. The ray and line equations already introduced in the vector math series can directly be used for collision detection. In fact, the line equation is very important and is used very often. The ray starts off at any point O in space and travels along a direction lambda times a direction vector r. The line in its Hesse form represented by an affine normal n can be used to test any point against, and we can gain the distance of that point to the line. Please check the video about rays and lines if you like to know more about the background and how to convert a ray to a line. The axis-aligned bounding box is represented by two vectors, a maximum Emax and a minimum Emin vector enclosing the inner geometric object. The minimum and maximum points are discovered by checking every x and y component of the enclosed geometry and performing a minimum and maximum function. The center is always at the half in between the minimum and maximum vectors. There are certainly other representations other than the min-max vectors, but we use this one here. Axis aligned means that the box is not rotated and its basis always lines up with the reference basis. As the circle, the AABB is a very coarse bound and tends to include a lot of empty space, as we can see in this example here. The rotated box is the inner geometry that needs to be tested, but the ABB really stretches out into empty space. So let's see how we can do better by using an OBB. As the name suggests, the oriented bounding box or OBB orients the box around the enclosed object. The bound might be tighter than the ABB but also requires more time to be computed and requires more processing to be done for transforming other points into its space. Speaking of the space, as we learned in the affine transformations, we can construct a OBB transformation matrix that allows to transform any point or vector into its space. Using the EX and EY vectors, we can not only construct the matrix but also the normals for the line that describe the OBB mathematically. Every of the introduced regions has its advantages and disadvantages. This video kicked off a series about collision detection for 2D games. In this video we discovered some basic collision bounds for testing 2D geometry. In later videos we will dive deeper into how those objects will be used and collided against each other. Thank you for watching. Until next time, stay safe, like, subscribe and comment. Bye now.